we're going to solve what I call multi-revolution problems. Okay. Solving multi-revolution problems, this is on page 575. We'll do the example in a bit, and we're going to look at how it gets affected. So the example that we're going to look at, and I'm going to write it down, it starts off with sine 3x equals 0. You can see something is going to be a multi-revolution problem by the fact that there's a horizontal stretch or compression inside the sine equation. So this one has a 3 beside the x. That's a multi-revolution problem because, and the reason I call it a multi-revolution problem is if you're used to solving between 0 and 2 pi, that means that if one x is between 0 and 2 pi, 3 x's will be between what and what? It's like if I asked you to pick a number between 0 and 10. Now I told you to multiply that number by 3. Where could your number now be between? 30 and, well, and 0. Does that make sense? If you picked a number between 0 and 10, and you multiplied it by 3, your answers are now between 0 and 30. So if our x was originally between 0 and 2 pi, and we multiplied that by 3, our new answer is going to be 0, between 0 and 6 pi. And if we think of our unit circle, that would be 3 times around. So then just let that sink in for a bit. Now that's part of the reason I call it a multi-revolution problem, because if one x is between 0 and 2 pi, 3 x's will be between 0 and 6 pi, which is like going around your circle. Oh, this for you is backwards. 1, 2, 3 times. So we call it a multi-revolution because we're going to be going around our circle more than one time. So when we're solving this, well, if it just said sine theta equals 0, if you had that instead, when is sine theta equal to 0? When theta is equal to, okay, sine is your y-coordinate. When's your y-coordinate equal to 0? At 0, at pi, and at 2 pi. Now, that's what you normally would do if it was sine theta equals 0 and you were solving between 0 and 2 pi. But now, what we have to do is we have to solve, because instead of having just theta inside, we have 3 theta inside. So that means 3 times around. If you were solving 3 times around, so instead of writing theta equals, inside is 3x, so we write 3x equals, and you would get 0, pi, and 2 pi, but that's just once around. On the second time around, what else will you get? Let's draw a little circle, see what we're doing here. Here's our unit circle. We're saying 0, pi, 2 pi. That's once around. On the second time around, we're going to hit 3 pi and 4 pi. That's twice around. And on the third time around, you're going to get 5 pi and 6 pi. That's solving for 3x. And all those answers for 3x are between 0 and 6 pi. If you wanted to solve for x, what would you have to do? If 3x is equal to pi, how do I figure out what x is? I need to divide by 3. So each of these answers, to figure out what x is, I'm going to need to divide them each by 3. So then x is going to equal, well, 0 divided by 3 is just 0, pi over 3, 2 pi over 3, 3 pi over 3, which you could write as pi if you wanted to, but you could leave it like that. And same thing with 6 pi over 3, and I'm going to change that one to 2 pi. See what happened after we divided by 3? What's our smallest answer? 0. What's our biggest answer? 2 pi. All of our answers now for x are between 0 and 2 pi, just like we wanted to begin with. So now that we've seen an example, to summarize, solving multi-revolution problems, what did we do first? We're going to change our domain, right? In this case, we changed our domain from 0 to 6 pi because it was a 3x. Can you see if it was a 2x inside, you'd go from 0 to 4 pi. So you're going to start with your domain as it was, solving between 0 and 2 pi. And if it's a 3x, well, we're multiplying everything by 3. We're going to look at 0 to 6 pi. We change our domain, and we do that to find out how many times we go around our unit circle. In this case, it's 3 times. So it's usually pretty simple. If the number in front's a 3, you're going to go around your unit circle 3 times. If it's 2, you're going to go around it twice. If it's a half, you're only going to go halfway around. So all of these things, whatever that value in front, tells you how far around your unit circle you're going to go. We then found all of our answers, right? Going 3 times around. We ended up with, how many answers are there? 7 answers. Once we had all 7 of those answers, we had to divide by that number in front with a coefficient. In this case, our number was 3. We had to divide each of our answers by 3. Our new answers are all between 0 and 2 pi as a result. Now, if the question said solve between 0 and 2 pi, you're done. If the question said solve over all the real numbers, you would then have to take all 6 of those and add 2k pi to them. So one thing you're going to do at the end is you're going to just check your domain. If it says you want to solve it over all real numbers, well, you've already solved it from 0 to 2 pi. If you have to do it over all real numbers, you have to add plus 2k pi to each one. So for example 2, we've basically already solved 2a, right? The only thing different in this example, solve sine 3x equals 0 over the domain from 0 to 2 pi. We've done that already. One thing I want to point out, though, is when looking at the domain, do you see that 2 pi is not included? Which is different than I wrote originally, because I originally wrote 2 pi is included. So when we got our final answer, when we got all 7 of those, for the textbook answer, we'd have to get rid of that one. because 2 pi wasn't included. But that's not hard, and in fact, one of the skills you need to start to develop is when you solve a question, you just want to check your domain just to make sure that it matches up with the answers that you have. Then in part B, it says state the general solution of the equation. Well, we've already solved it between 0 and 2 pi. So how we write our general solution, we can write it like this. X equals, and then do a big bracket and list them all vertically. So our first one was 0. Then we had pi over 3. Then 2 pi over 3. Then 3 pi over 3. Then 4 pi over 3. Then 5 pi over 3. And because 6 pi wasn't included, we could leave that one out. But generally, we list them all between 0 and 2 pi. So I'm going to include 6 pi over 3 as well. So I'm going to include every answer between 0 and 2 pi. Then to each one of those, yes, it is a little redundant, eh? We're going to add 2k pi to each one of those. You can draw a line and say k is an integer in the end. This is fine. This is right. We're also going to look at a way to write this a little bit shorter. But as far as a strategy goes, if you solve all of your answers between 0 and 2 pi, and then write them all out and add 2k pi to each of them, what that means is that's going to have everything that's coterminal with that one all the way through. So if we draw a picture of what we just did, and we have 0, and we have pi over 3, which would be about there, right? 2 pi over 3 there. We have pi. We have 3 pi over 3, which would be about there. 4 pi over 3, no. 3 pi over 3 there, 4 pi over 3, 5 pi over 3, and 6 pi over 3. Can you see that I hit that dot twice? So the 0 plus 2k pi starts at 0 and then goes around once and goes around twice and includes all the ones that hit there no matter how many times I go around positive or how many times I go around negative. The 6 pi over 3 plus 2k pi down there starts at the same place and does the same thing. This answer and this answer are redundant. So if you didn't have this, because it's already up there, it would still be right. Now, some mathematicians would also say, well, you could also say, since I have this one, and then this one, 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 instead of doing those two separately, instead of having 0 plus 2k pi and pi plus 2k pi separate, I could have just done 0 plus k pi, and that would go halfway around the circle and include them all. So there are some ways that we could make this more efficient. In order to make it the most efficient, I'm going to show you another technique. When you solve these multi-revolution questions over all real numbers, you can choose one of these two techniques. This first technique that we did, the technique was solve between 0 and 2 pi, find all of our answers by changing our domain to see how many times we need to go around, and then divide to find all of our answers between 0 and 2 pi, then add 2k pi to each one of those. That was method 1 for general solution. If we want to do the general solution, method 2. Now this is only for general solution. Would you like to do a new example, or do you want to do the same one? A new example? Okay, so let's say we do cos of 2 theta equals negative 1/2. Something that's on our pie plate. Method 2. I'm going to leave space here to do method 1 again. Would you like to see method 1 again since it's fresh in your mind just to get it first, or do you want to go directly to method 2 and review method 1 after? Method 2 to start? Okay. So we're doing method 2 to start. What we do in method 2 to start is we solve things like we would a general solution normally. If it was a general solution normally, you would have written whatever angles inside equals, done these brackets, and just said, well, when is cos equal to negative 1/2? It's part of my pi over 3 family. It's negative, so it's in quadrant 2 and quadrant 4. So what are my pi over 3 families in quadrant 2 and quadrant 4? They would be 2 pi over 3. Oh, quadrant 2 and quadrant 3, sorry. And 4 pi over 3. And you would have done plus 2k pi plus 2k pi, where k is an integer. That's how you would have solved it if it was just, you know, if I had an x in here instead. You would go x equals, write your two answers, and then plus 2k pi, and you would be done. But instead of an x, we have 2 theta. So how do I get theta? I need to divide by 2. So nice thing about method 2 for the general solution is now we need to divide both of these by 2. And when you divide them by 2, can you see that the first one just becomes pi over 3? But instead of adding 2k pi, you divide that by 2 as well, you'll just have plus k pi. 4 pi over 3 when you divide it by 2 becomes 2 pi over 3. And instead of adding 2k pi, you're adding k pi. We're going to look at what does this mean. On our unit circle, first of all, pi over 3 is here. Okay? And 2 pi over 3 is here. Now what's going to happen if I add pi to this one, pi over 3? It's going to go halfway around the circle. And it's going to go here, and then back in this one, and then back in this one, and then back in this one. And it'll go between those two forever. And what's going to happen to this one when I add pi? It's going to go to quadrant 4 and get that pi over 3 family, and then go back in this one, and back in this one, back and back and back. And that's what that solution would look like. You would have those 4 answers between 0 and 2 pi, and have everything that's coterminal with them. Now when we did method 1, we did the same thing. Method 1, as a review, I said I'd do this question with method 1. We first said, let's solve between 0 and 2 pi. So if I'm solving for theta between 0 and 2 pi, then 2 thetas is going to be between 0 and 4 pi. And that's going twice around. Going twice around, I'd say, well, the first time around, when is cos equal to negative 1/2? Well, that is at 2 pi over 3 in quadrant 2 and 4 pi over 3 in quadrant 3. The second time around, does it make sense that I'm going to add 2 pi to 2 pi over 3? And 2 pi is equal to what over 3? 6 pi over 3. Because 6 pi over 3 is the same as 2 pi. If I add 6 pi over 3, and the reason I changed it to 6 pi over 3, so when I add it to this, I have a common denominator. And then this just becomes 8 pi over 3, and adding 6 to that one becomes 10 pi over 3. Those are my answers between 0 and 4 pi. Now when I divide everything by 2, I get pi over 3, 2 pi over 3, 4 pi over 3, and 5 pi over 3. And now when I write my general solution here, I would list all 4 of those and add 2k pi to each one. Where k is an integer. If we look at our unit circle, can you see that that's all 4 family members of pi over 3? Is that not what we drew? But now, instead of counting just 2 of them and going halfway around the circle, this way is counting all 4 of them separate and going all the way around the circle and doing all of those coterminal ones separately. So you have a choice. If it's a general solution question, you can use method 1 or method 2. As far as making your life a little bit easier, then I would say go with method 1, because sometimes you're going to be asked to solve between 0 and 2 pi. And if you're asked to solve between 0 and 2 pi, you need to know up to here of method 1 no matter what. And if you know up to here on method 1, then the general solution just means add 2k pi to every answer you've got. You can do it without thinking. If you want to use the shortcut idea, well, you already know how to solve the general solution by adding 2k pi. It just means you have to divide everything by whatever that number is in front. So if it was 3 theta, you'd have 2 pi over 9 plus 2k pi over 3. And you divide everything by 3. It makes your final answer a little bit more elegant because it's not as big to deal with. But that doesn't matter. They will accept your answer in any form on the final exam. So you get to choose that way. Multi-revolution questions to practice, 5, 6, and 10.